Hello and welcome back to Calculus 1, section 3.3 on rules of differentiation. So what do we have here? Remember how, in those darkest hours of your life so far, they shove the entire multiplication table down your throat? And you've just been there for days, memorizing the whole thing, going, why? Well, because we can be lazy if we know multiplication table, right? Instead of writing 3, why red? 3 plus 3 plus 3 plus 3 plus 3, and then computing that as 3 plus 3 is 6 plus 3 is 9 plus 3 is 12 plus 3 is 15, we get to memorize the shortcut 3 times 5 is 15 and be done with it, right? So what is multiplication table? Multiplication table is an excuse to be lazy, right? It is a fast way to do repeated addition, and we do it so that we can be lazy and save on time. Now you can be even lazier with your calculators, right, and cell phones. Now that also works for, let's say, 231 times, 16. You don't have to know how to multiply this. All you need to do is to add 231 16 times. So you go, okay, 231 plus 231 is 462 plus 200, right? You get the idea. And as you add these, you add them 16 times and you will have the answer, right? So no, you don't need to know, you don't need to memorize multiplication tables. But at that tender age, right, when you were like, 8 years old or whatever, some people said, no, you have to memorize this. And then you dreaded your life, but you did it, right? Because you want to survive, right? If you don't do what adults tell you, they just stop feeding you and they get a better kid out of it. That's all. Too dark for the beginning of the class? All right, we'll wait then. I had more material. So this is what 3.3 is. Convenience section. We know how to take the derivative. The derivative is f prime of x is equal to the limit h goes to 0 of f of x plus h minus f of x divided by h. This is the formula that we crank every time when we want to find the derivative. But then through time, people figured out that we actually don't have to do this formula because there are certain rules that give us answers, like the patterns, and we can just memorize those and really not use this formula ever again. So now we are at this point where we are making a trade-off. Do you want to memorize stuff, or you want to crank this every time? If you want to crank this every time, well, come back for chapter 4. There's nothing else in chapter 3 I need to tell you, okay? Because this section is about polynomials and constants and some basic rules. The next section is on trig. The section down the line would be on inverse trig and exponential and logarithmic derivatives. So we are learning differentiation rules the entire chapter. And if you don't want to memorize those rules and shortcuts, well, check out and then come back when we start chapter 4. I mean, if we have exam, obviously stop by that too. That will be helpful, right? But yeah. So what are the things that we are memorizing? Well, we are memorizing that the derivative of a constant is is 0. Good. Why is the derivative of a constant 0?
Because the slope is 0.
Because the slope is 0. Well, yes. So constant is the function that is flat, and the tangent line m tangent is equal to 0, so derivative is equal to 0. That's one way. Can anyone else tell me another reason why would the derivative of constant be Good. There is no change. Very good. So I heard you also say that. So derivative measures change, right? What is the change in constant? There is no change in constant, right? Those terms are mutually exclusive. Stuff is either constant or is changing. So the derivative of constant is 0 because there is no change. Great. So now that means that all of these examples, like the derivative of 5 is 0, the derivative of negative 7 is 0, the derivative of pi is 0. So all of these are 0 because you are taking the derivative of a constant. Now the next rule covers much more than it meets the eye on the first run. Is anyone catching that reference now? I don't see your faces. More than meets the eye? Transformers, there we go, nice. And that is x to the n, which is n, x to the n minus 1. So you are memorizing this formula. So these are the big formulas. They're going to get these pink boxes. You will be using these formulas all the time for all of your courses to come. So what is this cover? Well, can you tell me what are all of the things that I can stuff into this n? Okay, whole numbers. So that would give me x squared, x cubed, and all of that. What else I can put in there? Fractions. Now what would that give me? Square root if it's 1/2. Or any root, exactly. 1 over n is the nth root. So with this one I can calculate that. And there's one more thing left. Negatives. What would that give us? 1 over x squared and x cubed. This formula covers a lot. This formula covers, so hold on, this will be so dramatic. So if the exponent is negative, right, we have situation like 1 over x to the n. Those are rational functions. If the exponent is positive, we just have x to the n. That's the polynomials. And then if n is equal to a over b, you have x to the b root of x to the a. This covers all of the roots. It covers rational function and polynomial functions. So this one rule covers a lot. So now, if you are looking at your old questions, what is the derivative of x to the 7? Seven x to the 6, very good. N is equal to 7. You plug that for each n on the other side of the formula, and you get 7x to the 6. Shall we go and think about the x plus h solution? It would be x plus h to the 7th power. Right? Go fold. Right, go foil. Foil that. I'll be back on Thursday to see if you got this 7x over 6. Right? So the idea over here is, again, save time, save energy by memorizing these formulas so we don't have to deal with the limit. Right? Make the piece. And you did the same thing for multiplication earlier in life, but others made that decision for you, right? Because you were too young. Now, you as adults get to make the decision to memorize these formulas so you don't have to mess with the limit every time you need to take the limit. What is the derivative of 4th root of x? So we are going to rewrite this first using algebra. This is the derivative of x to the 1/4. Very good. And now, unleash the formula. Your n is 1/4, so that goes 1/4 in front. X raised to the 1/4 minus 1, which is negative 3/4. And you're done. That's that. Now you can make it pretty. Say 1/4 times 4th root of x cubed. Right? If you really want to be special, there you go. You do that. Now clearly you keep this form if you have further calculations. You don't want to be working with the 4th root flying around. So just you leave that for. All right, and there is another one. What is this one? No. 1/x to the 9. We have to rewrite this first. So the derivative of what? All I heard is x to the. Thank you. X minus 9. That's good. So now we drop down negative 9. We have x, and then minus 9. This is usually where stuff goes wrong. It's negative 9 minus 1 is negative 10, exactly. So if you have an 8 over there, just go and fix it before anyone else sees it. You are always subtracting 1. So 7 minus 1 is 6. And over here on the bottom, negative 9 minus 1 is negative 10. So yeah, you go more negative. To make this pretty, we put negative 9 over x to the 10. Again, we use this for calculations, for further calculations and further derivatives. So one rule covers all of these cases, and this is a very useful and very frequent rule. Most of your functions are there. You have polynomials floating around your math problems. Now we have some of the rules that help us solve more complex stuff, because functions are not always just x squared or 1 over x or something like that. Functions are sometimes combination of these things, and we need to work through the two, or you can call it 3 also, formulas that will help us with these more complex situations. So these are the properties in some sense. We have that the derivative of sum of two functions is individual derivatives of these functions. And same for subtraction. So I'm just going to force one more formula in the same line. So this is the addition property, and also works for subtraction. And this will help you to solve a derivative problem where you have, let's say, x squared plus 3x minus 9. So you have, multiple functions within a larger function. You have x squared function, you have whatever I said, 3x function, and a constant negative 9 function. So those are 3 quadratic linear and constant, right, which is also linear function. And all this blue rule says is that you take the derivative of each one of those functions inside separately. If they are separated by plus and minus, you take the separate derivative. The last one is when the function is pre-multiplied by a constant. I should just say multiplied by a constant. You can kick that constant outside. And this is what we have, right? This is what we have. So this would be good if you have, let's say, 3x squared. That 3 in front of x squared is the constant. So you can ignore it and just take the derivative of x squared. And then you will multiply it by that 3. So to use this rule, the one on the bottom, if you have the derivative of 3x squared, you will ignore the 3 and you will just focus on the derivative of x squared, and then when you get that 2x, it will multiply into 3 and get you 6x on the final answer. So what we have over here is a rule that says that you can keep the constant outside. We had the same rule for limits. You can keep the constant in front of the limit, and we are going to have the same rule for integration in chapter 5, where you keep the constant in front of the integral. You deal with the stuff inside, and then at the end times that constant outside, and we're good to go. So all of these things work. Great. Now I would like to do a problem which will take all of these, both of these rules, and have it in this one single example. So what is the derivative of, and now I have, let's go with 3x to the 4th minus 2x squared plus 4 over x to the 6th minus square root of, just minus 10. There we go, I'm done. Every time you have this coefficient, which is 3 and negative 2 and positive 4, you get to ignore them and just deal with the function. But now you have to realize that the first rule that I have up there, which is f of x plus g of x, right? That rule kicks in. So this is 4 separate problems to solve because we are using our rules from before. So we only have 2 rules so far. Rules for all other functions. It's coming up. The entire chapter is just devoted to that. We just learned now 2 rules. The constant rule, the derivative constant is 0, and then the polynomial one, which covers a lot of other stuff as a square root and so on. So we have 4 separate derivatives that we have to take. Now, I'm going to write a line that you will never write again once you figure out what these derivatives do. But, it's a teaching strategy, so I do it. 3, and then we take the derivative of x to the 4th. Then we have negative 2, kick out. Then the derivative of x squared. Then we kick 4 out. And we take the derivative of x to the negative 6. And finally, we take negative out, and we take the derivative of the constant 10. So what I have done here is I went from the long expression, that 4 terms, into 4 individual derivatives on basic functions, which we all covered in those first 2 formulas. What is the derivative of x to the 4? Very good. Right? Your n is 4, so that goes in front because it's n x to the n minus 1, right? That's the formula. So n is 4, so it goes in front. Now I still have to multiply 3 times 4, so make sure that's not a 34 there, it's 3 times 4. Minus 2, and what's the derivative of x squared? 2x. The derivative of x squared is 2x. Maybe I can put these parentheses where the derivatives go. Great. Plus 4, and now I have x to the negative 6. So what's happening there? Negative 6x to the negative 7, right? We go more negative. And finally, the last one is?
0.
Yes. Minus 0 plus 0, whatever. All I need to do is to clean this up, and we're done. 3 times 4 is 12. So we have 12x cubed minus 4x minus 24 over x to the 7, because I want to push that in denominator. And then the minus 0, who cares? So this is my derivative for the function that I wrote up there. Obviously the 10 at the end dies because it's constant, right? Derivative of constant is 0. So that takes care of that. So I hope you see the way these rules are used. Right? If you have addition or subtraction of functions, you are allowed to assign the derivative to each one of those. We have the same rules in limits. We just haven't used them. We should have, but we haven't used them as much. For derivatives, you will be using this a lot. So make sure you are familiar and comfortable with these two formulas, including the formula where, not formula, yeah, I'll just leave it at there. Well, we'll cover more. All right, so the next one is another formula that we are memorizing, and this is the derivative of exponential function with the e being the base. So what's the derivative of e to the x? The answer is e to the x. This is the only function that does this. Function is equal to its derivative, point for point. Now, even though, well, I'm not supposed to, you know what, I'm not going to box this one because I should box that one. All right. So, I'll give you the formula that you will be using most of the time. So the derivative of e to the ax. So this is the formula that you will be using most of the time. And that is a e to the ax. So you see there is always this component of rewriting e just as it is and then going on with the rest of the stuff. So now you are getting this, and this will be explained next week. So, yeah, tough luck. So I'm going to box this one too, because it's important. It's important calculation. So what is the derivative of e to the 6x? What is the derivative here? 6e to the 6e to the 6x. Good. So now these are examples over here. How about the derivative of 3 times e to the 5. I see a smile. It's confirmation that it's going well. All right. What do you guys think?
3 times d over dx.
Okay, you can kick the constant out, and you would have e to the 5, right? So it's not a fair question, but whatever. So it's 3e, but no. Well, I'll just go with the answer. Answer is 0.
I don't like that one.
What's e to the 5? It's constant. Times 3, still constant. I know, right. See that? Now you see it. Let's see. How about if I had 4e to the pi?
That's still 0.
It's still 0. All right, cool. I can't trick you there, huh?
Made it clear the last one.
Let's see what happens at the exam, huh?
Oh, trust me, I'll forget.
By that time, events quickly. So. So, I'll write the formulas that are formulas to be memorized. We have the derivative of constant is 0, the derivative of x to the n is n, x to the n minus 1. Then we have the derivative of f plus g or minus g is the derivative of, well, I can just put f prime and g prime. So f prime plus minus g prime. You can use that notation as well, fine. And then we had constant can be kicked outside. So c times f is c, derivative of f. And finally, I'm going to write the one that is mostly used, which is e to the ax or a e to the ax. So these are the formulas that you have to memorize so far. Now, obviously, this is going to grow in every section because we are going to add 6 trigonometric functions. 6 inverse trigonometric functions. We have ln's and logs and other things. You know what the cool realization is? Even though you have so many, it's not going to be 100 of them. Like it was 100 for multiplication, right? Because at that point in time, commutative rule was not in your head to immediately know that 3 times 5 is 5 times 3, right? So you went there and you invested time into memorizing that 3 times 5 is 15 and 5 times 3 is 15. Independently of each other, right? Because otherwise you will have to learn half of the multiplication table, right? But no, you memorized all 100, right? So now, guys, I gave you 6 formulas so far. Please remember this is a double formula because it's one formula for plus and one for minus. So I gave you 6 formulas so far, and that's pretty much it. Now we also have to talk about some other things in this section, but before we do that, let's go and have another example over here. So now this is the derivative of 3e to the 4x minus 10x squared plus 9. Yes, we need to accept cookie then, yes. Send it. Accept it. Timekeeper, what time are we going home?
35 minutes.
Hey. Oh. Self-identified, right? Okay. So what do I have? What's the first one? 12. E. 4x. Okay. Come on, Flash, let's go.
Oh, like a whole, minus 20x.
All right. That's it. Good. Well, maybe we can put it here. 12e to 4x minus 20x and be done. Did you catch the Flash reference? Ha. 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 All right. Higher order derivatives. Those of you who haven't seen it, you have no clue, but you missed a lot. Higher order derivatives. I can have derivative on top of the 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 derivative. Application demands it. We're going to have an entire section where I'm going to say there's a path function, and when you take the derivative of that function, well, change of position in time is called velocity, because when you write change of position in time, you have position miles and time hours, you get miles per hour. So the derivative of position function, this is not what we're learning tonight, but it's good thing to kind of start off what we are looking into. So the first derivative of position is going to be velocity. But then you can change the velocity by pushing on your gas or brake pedals. And change of velocity is called acceleration. And when you are going the other way, we call deceleration, but it's still acceleration, the minus sign in front. So technically the two pedals you have in your car is, the two pedals that you have are both acceleration, one positive and one negative. If you have a car with 3 pedals, please upgrade. It's over, it's like horses, all right? No, you want a third pedal because you waste more fuel. Fine.
It's more fun to drive.
How is it fun to drive when you're in traffic? Like, constantly. Like, that's how you get arthritis in your hand. That's it. I mean, anyway. So, higher order derivatives. I just mentioned the first and the second derivative. There's also a third derivative in that mix that we'll mention and so on. So what can I do? Well, please remember that when you take the derivative of a function, you get another function. What is the derivative of x squared? 2x, right? 2x is a linear function. Can you take the derivative of that and get what? 2. Now 2 is what kind of function? Constant function, right? What's the derivative of that? 0, right? So we kind of killed x squared after so many derivatives. So we see now that, so we'll have a full lecture on this. I'm erasing it, it's not important now. Application demands to have multiple derivatives. And we're just going to call these first derivative, second derivative, third, fourth, and so on. So I'm going to have f prime of x to be the first. Well, actually, let's start with just f of x. F of x is our original function, right? Like x squared, I mentioned. And then you're going to have f prime of x, which is the first derivative. And you know how to take that derivative and just go and use the rules we learned. shortcuts. Or if you like pain, use the limit. It's fine. So this is function. And then we have the first derivative. The second derivative will have two tick marks, right? Two primes. And then there will be the second derivative. The third derivative will have three of these. The fourth derivative will not have these tick marks. We switch notation into the number in parentheses, not to be confused with f to the fourth power. So that's exponent on the function. And this is the fourth derivative. So these are the two different concepts that are very close in notation, and now you understand why you have to have those parentheses. Otherwise you're doomed. You don't know if it's a fourth derivative they want, or they're saying f to the fourth. Right? So be very careful about that. So, fourth derivative, and then 5 for the fifth derivative, and so good effort. And so these are the higher order derivatives. And you just go and take them all in order. I mean, you can't go and find the fifth derivative directly, unless it's some kind of special case when it's obvious. Right? You have to go through first and second and third and fourth to get to fifth derivative. Because every derivative in this string of derivatives is the first derivative of the previous line. Right? And you know the formulas for the first derivative. Can we invent the formulas for the sixth derivative? Maybe, but no one wants to do that. Why would you invest time in developing something when you can just keep taking first derivative until you get what you want to be? Plus, application never calls for the fourth and fifth and seventh derivative, right? Because there's no need. Application calls to up to 3 derivatives. I've seen a 4 derivative application once in graduate school. That was it. On a seminar, not as a part of my class, but as a seminar, which was some research done, and the professor who gave, he was taking the 4th partial derivative, right? And then I said, okay, this is the first time, because generally it's up to the 3rd derivative, which is why the notation changes, right? The application, this has to be application driven right here, because technically you have your position. And we'll see how this works when we put this applied wrapper on it. And that's, I think, next class or the following class. It's going to be that. So lecture after this is product rule, and then after that is trig integrals. And then should be the lecture that talks about velocity and all these cool things. So, as an example now, we're going to take a look at f of x as, let's say, 4x cubed. And we want to take all the derivatives we can. So what is the first derivative? F prime. Air conditioning is on and you have no microphone. So when you say in that tone, all I get on this side is blue.
12x squared.
12x squared, thank you. What is the second derivative? 24x, thank you. How about the third derivative? 24. How about the fourth derivative?
0.
Okay. How about the 163rd derivative of x? 0, because they all have to be 0, right? So once is that. Great. So you have the idea of what these higher order derivatives are. Higher order derivative is always the first derivative of the previous order you had. So the fourth derivative is the first derivative of the third derivative. Third derivative is the first derivative of the second derivative. Second derivative is the first derivative of the first derivative. And finally we have the first derivative, which is the first derivative of the function. You can unwrap this. So fun question. F of x is equal to e to the x. What is the 24th derivative of f of x? E to the x, right? It's e to the x because every time when you do the derivative, well, e to the x derivative is itself, e to the x. So it doesn't matter if you do 24 derivatives or 124 derivatives, it will always be e to the x. The interesting question that makes you think a little bit is, let me switch this and have it as e to the 2x. What is the 24th derivative now? Nice. 2 to the 24th e to the x. See, every time when you take the derivative of e to the 2x, the 2 will pop in front, right? Because we have the rule, it's a e to the ax. So the 2 will show up. Well, you will do that 24 times, so 24 2's will be there. So that's why it's 2 to the 24th power. If you start taking these derivatives one by one, it will make more sense. F prime is 2e to the 2x. F double prime is 2 times 2 e to the 2x. Now note that you have a second derivative and you have two 2's. Copy the constants. 2 times 2. Now you're taking derivative into the 2x, another 2 pops down, and you have this. So now it's a third derivative and 3 of these. So you see that the order of the derivative is exactly the same as the number of 2's. So if the 24th derivative is the 24th exponent on 2. Yes?
Would you drop the 24th? Or is it get there?
Oh, I didn't write, yeah. There is a 2x over here.
I was like, oh, you said something and I didn't hear it.
No, it's clearly a 2.
No, you're right.
Look. 2. That's it. Bye.